with a little bit of background in redox reactions, now we can actually go through the process of writing net redox reactions. So we've listed the steps for that here. Now first, with the given problem, you want to locate the reactions in the standard reduction potential table that includes the given components. So once you do that, you want to list these reactions from the most negative potential to the most positive potential. So the way that you will be writing these then will be as they appear from the top of the standard reduction potential table to the bottom. So you will write those in that order. For step 2, we want to imagine that the components on the left of the reaction arrow have empty orbitals, and the components on the right of the reaction arrow have orbitals filled with electrons. This will be necessary in order to understand the spontaneous movement of electrons. For step 3, now that we've listed our reactions, we want to circle the species that are actually present. For step 4, what we will do is identify any movement of electrons from high energy orbitals to low energy empty orbitals. If we do not have that type of movement from electrons of higher energy to that of lower energy empty orbitals, then we would have no spontaneous redox reaction. In step 5, assuming we have identified that we have a spontaneous redox reaction, of the 2 reactions written, we need to take the top reaction and reverse it. And that is because the top listed reaction is the reaction that will occur as an oxidation. And when we are looking at reactions in the standard reduction potential table, those are written as reductions. So we will need to flip this top reaction to show it occurring as an oxidation. Lastly, with step 6, we need to add these 2 reactions together in a way in which the electrons will cancel. Now sometimes this means that you may have to take one of these reactions or both of these reactions and multiply them by a number so that the number of electrons in each half reaction will cancel. Before we go through an example, I wanted to demonstrate what I meant by saying imagine that the components on the left of the reaction arrow have empty orbitals, as I've indicated here by the tin 2+ and lead 2+ aqueous ions. And we want to visualize that the components on the right of the reaction arrow have electrons filling the orbitals, as I've demonstrated here next to potassium solid and sodium solid. So we want to visualize filled electrons in orbitals to the right of the reaction arrow and empty orbitals next to the components on the left of the reaction arrow. So let's go through an example. Write the net equation for the reaction, if there is one, when hydrogen gas is bubbled into a nickel 2 iodide solution. So here we're showing hydrogen gas in nickel iodide aqueous solution. So considering I've been given a solution, the first thing I want to do with this is check my solubility rules. And in fact, nickel 2 iodide is a soluble ionic compound. So this will exist as separate aqueous ions. So what we really have in this example is shown here. Hydrogen gas, nickel 2+ aqueous ions, and iodide aqueous ions. So now that we've identified what we were given in this question, we need to find the reduction potentials associated with these reactions in the standard reduction potentials table. And so what we want to do here is actually list these in the order from the most negative potential to the most positive. So we want to identify the reactions that include the components that we've identified we are starting with. So if we do that, this is what we come up with. Notice that first I encounter the reaction including nickel 2 plus with a potential of negative 0.23 volts. So I want to write that one at the top. I want to write that one first. Then I come across the reaction that includes hydrogen gas. This is the standard hydrogen electrode, and this has 0 volts associated with it. So we put that below the reaction including the nickel 2 plus ion. And lastly, the reaction that includes the iodide ion is listed with a potential of positive 0.54, so that we will put at the bottom. So we have effectively written these from the most negative potential to the most positive potential. So for step 2, we are now saying we want to imagine that the orbitals to the left of the arrows are empty and the orbitals to the right of the arrows have electrons. So here are our empty orbitals and here are the filled orbitals. So with this picture in mind, now we can circle the species that are actually present. So we said that we had hydrogen gas, we had nickel 2 plus aqueous ion, and we have iodide ion. So here is the nickel 2 plus, here is the hydrogen gas, and here is the aqueous iodide ion. So once we have circled these components, we want to go ahead and mention that we won't be considering the other components within these reactions because those are not present. We are not starting with those. In the prompt that we were given, we were starting with aqueous nickel 2 plus ion. We did not have nickel solid. So we can ignore the components that are not actually present. So now that we've identified this, we want to see if we have any spontaneous movement of electrons. So what we actually have in this example is upwards movement from electrons of lower energy to an empty orbital that is higher in energy. So neither of these movements would be considered spontaneous. So this is an example of a reaction that has no spontaneous movement of electrons. And we could say that this results in no appreciable reaction, meaning that we do not have a spontaneous reaction. So let's go through another example. Write the net equation for the reaction, if there is one, when hydrogen gas is bubbled into a copper 2 iodide solution. We are told that we have hydrogen gas and copper 2 iodide solution. So again, looking at our solubility rules, we can confirm that copper 2 iodide exists as an aqueous solution. So we have aqueous ions. So including this, we now have hydrogen gas plus copper 2 plus aqueous ions plus iodide aqueous ions. Identifying those components, we now want to look at where they can be found in the reactions listed in the standard reduction potentials table. So doing that, we first encounter hydrogen gas. This is a potential of 0 volts. As we go down the table, we come across the next reaction, including our copper 2 plus aqueous ion, which has a potential of positive 0.34 volts. And lastly, we come across the reaction that includes the iodide ion, which has a potential of positive 0.54 volts. So we write these in the order from the most negative to the most positive. We can go ahead and place empty orbitals to the left of the reaction arrows and filled orbitals to the right of the reaction arrows. We can go ahead and identify the species that are actually present. We have hydrogen gas, copper 2 plus aqueous ion, and iodide ions. Here I've circled where those exist in the written reactions. With that, we now can identify all the possibilities of electron movement. If I start with my iodide ions, I would be looking at a transition of electrons from lower energy up to an empty orbital that is higher in energy. And we know that this is not a spontaneous movement of electrons. However, if I look at the hydrogen gas, I see that I have electrons of higher energy that can move to an orbital of lower energy that exists with copper 2+. So this movement of electrons is downhill and therefore is spontaneous. So these two reactions are the only ones that will participate in the net reaction. Therefore, we can identify the iodide ions as being present as spectators. They don't actually participate in this redox reaction. Now that I've identified the two reactions that are participating in the net redox reaction, I will go ahead and take the top reaction, which is the one that has the more negative potential associated with it, and I will reverse it. And that is because the reaction that has a more negative potential is the one that will occur as an oxidation. So taking the reaction as written, where it is written as a reduction reaction, I will flip it to show that it is an oxidation reaction. Remember, we had mentioned that in oxidation reactions, we see electrons are products, where in reduction reactions, electrons are reactants. So here I've written my oxidation half reaction, and the bottom reaction can just be rewritten as is because it participates as a reduction reaction. Doing so, I have these two half reactions that I will be adding together. Now in this example, I see that I had 2 electrons produced in the oxidation half reactions and 2 electrons present in the reactant side for the reduction half reaction. So these 2 electrons will cancel. Once they have canceled, I will go ahead and add all of the reactants together and all of the products together. And whenever I do this, I want to make sure that I write the oxidizing agent first, as shown. So I will write my net reaction as copper 2+ aqueous ion plus hydrogen gas, producing copper solid and aqueous hydrogen ions. So before I do the next example, I want to remind you that we had listed strong acids that actually ionize when you put them into water. And one of those examples was hydrochloric acid. We take hydrogen chloride and dissolve it into water, we will actually produce aqueous hydrogen ion and aqueous chloride ion. Whenever we have aqueous hydrogen ion present in solution, we would say that this is an acidic solution. So this is important to keep in mind when we're reading these types of word problems. So with the next example, write the spontaneous net equation for the reaction, if there is one, when a copper-coated zinc penny is placed in an aqueous solution of HCl. So we're told that we have copper solid that is coated with zinc, so we have copper solid and zinc solid, plus aqueous HCl. Again, we first want to look at our solubility rules. HCl is listed as a strong acid, so it will form ions when placed into water. So what we really have present is copper solid, zinc solid, aqueous hydrogen ion, and aqueous chloride ion. So these 4 components are present in this example. If we are asked what gas is being given off, we will have to look at the net reaction. I have the possibility of giving off hydrogen gas or chlorine gas, but I won't know until I write the net reaction. So given these 4 materials, I will have to look up 4 reactions that correspond to these materials, and I will be writing them from most negative potential to most positive potential. So when I do that, we see that they are written in this way here. So these are written in the correct order from the most negative potential, that with a negative 0.76 volts, to the most positive potential, that of positive 1.36 volts. Now that I've written them in this order, I can imagine the empty orbitals to the left of the arrow and the filled orbitals to the right of the arrow. Now I can circle the species that are actually present. We have copper solid, zinc solid, aqueous hydrogen ion, and aqueous chloride ion. So here are the 4 species that we have present in this reaction. Now we want to identify any spontaneous movement of electrons from higher energy orbitals to lower energy empty orbitals. And I see that in this example, I only have 1 empty orbital, that of which is present in the reaction with aqueous hydrogen ion. So the only spontaneous movement of electrons will be from that of zinc to that of the aqueous hydrogen ion. So the top 2 reactions are going to be the ones that participate in the net redox reaction. So with these, I will have to reverse the top reaction because it will actually occur as an oxidation. So doing so, we get this. Again, we can identify that this is an oxidation because electrons are on the product side of this reaction. The reduction half reaction will be written as is, as can be seen in the standard reduction potential table. In this reaction, we had 2 electrons on the product side in the oxidation and 2 electrons in the reactant side of the reduction, so these cancel out. And so lastly, when I'm adding these together, I want to make sure that I put my oxidizing agent first, so the components in the reduction half reaction will be first written on the reactant side. So when I do that, this will be my net reaction. 2 aqueous hydrogen ions plus zinc solid, yielding hydrogen gas and zinc 2 plus aqueous ion. So to answer the question, the gas that is given off in the spontaneous reaction is hydrogen gas. And you can visit this link to see this reaction occurring.